Today we're going to continue talking about set theory. In particular, we will talk about what elements of a set are, how you denote elements of a set, and counting elements. As we discussed last time, the elements of a set are simply the objects in that set. The symbol for denoting an element is given below, and it sort of looks like a little E. For example, if we take A to be the set 1, little a, little b, and 2, we can say that 1 is an element of A is an element of A, B is an element of A, and 2 is an element of A. But we couldn't say that 3 is an element of A. Notice that I have the element sign with a bar slash through it for not an element of. It'll be important to remember that this is the symbol for an element, and an easy way to do that is that since the symbol looks like an E, you can think that E is for element. Secondly, the bar going through the element sign, it's easy to remember that that means not an element of, because we've already seen this with equality signs in college algebra or high school algebra. The next topic involves counting the number of elements, and we'll begin with a simple example. The elements of a set are just the objects in that collection. So below we have a collection of green dots. However, I have another collection of green dots on the right. And so as collections they are the same. These are the collection of green dots. And so as sets they are the same. We say that two sets are equal when they have the same elements. What's important here is that I do not specify the number of elements. For example, if we take set A to be the set of elements A, B, and C, and B to be the set consisting of A, B, B, and C, and we take C to be the set consisting of A, D, and C, we can say that A and B are the same set because they both contain A, they both contain B, and they both contain C. However, set A and set C are not the same. For instance, A contains B and C does not contain B. And B and C are also not the same set, so they are not equal. And again, for the same reason. Set B contains little element B, and C does not. When determining when two sets are equal, the number of elements does not matter. And that is why we are able to say that set A, consisting of A, B, and C, is the same or is equal to the set consisting of A, B, B, and C. Again, here's another example. Here we have a set on the left with number 1, and on the right we have a set with 5 number 1s. Yet as sets, they are both equal. They are the set containing the element 1. Because we're looking at counting the number of elements, this brings up this idea of cardinality. The cardinality of a set, which is denoted N of A, is the number of distinct elements of A. What's important here is that we have the word distinct. So if we go back to the last example where we had the set 1 with 1 1 on the left and the set consisting of 1 with 5 1s, those both have one distinct element, which happens to be 1. Here's another example. Let's take A to be the set consisting of 1, 1, 1, B to be the set consisting of 1, 2, 3, C will be the set consisting of nothing, in other words, C has no elements, and D will be the set consisting of 1, 1, and 2. If we want to find the cardinality of each of these sets, notice that A has one distinct element. It has the element of 1. B has 3 distinct elements, so its cardinality is 3. C has no distinct elements, so its cardinality is 0. And the set D has 2 distinct elements, so its cardinality is 2. The set that we just saw on the last slide, the empty set, is the set with no elements in it. And the empty set is actually pretty important, and it'll come up later in other slides. It is so important that we actually have 2 ways of denoting it. One, we can use our set notation with the curly brackets, or we could use another notation which is almost like a 0 with a slash through it. That means the empty set, and those are equivalent. Last time we saw a set that consisted of infinitely many numbers. It was the set of positive even numbers. And we showed that we could list the elements of the set as 1 or 2, 4, 6, 8, and then once we have a pattern established, we can put those dots. This was an example of an infinite set because its cardinality is infinite. However, we also have this idea of a finite set, and that is when the cardinality, or the number of distinct sets as distinct elements, is finite. So an example of a finite set would be 1, 2, 3, and 4. Alright, that concludes the lesson for today. Next time we will talk about taking subcollections of sets.